Hi everyone, welcome to lesson 16 of the Advanced Higher Stats course. In this lesson, we will be looking at fitting a linear model on bivariate data. You will find this skill on page 30 and 31 of the Advanced Higher course spec. By the end of this lesson, you should know if a linear model can be fitted in a scatter plot by just looking at them. You should be able to calculate the squares regression line of y on x and x on y. And you should be able to calculate s double x, s double y, and sxy. So just to clear up any confusion, bivariate data are observations involving two paired variables. So like height and age, they relate with each other. And linear model is a straight line that represents the relationship between two variables. Similar to how in higher or Nat 5 maths, you did y is equal to mx plus c. We have a similar one where we have this epsilon as well, and we'll get to that later. Now, I would like you to answer these questions. Describe the correlation of each of these graphs. Okay, so here I would say it's a strong positive. Here I would say it's a weak negative. I'd say there's no correlation here. This is a strong negative. And this is a weak positive. Now let's look at epsilon. Epsilon is the difference between the true value and the estimated value, and it's often referred to as a residual. What this means is, here we have a graph comparing weight and height, and we have this linear model which we've implemented. And maybe this linear model says that a person who's 6'4" weighs 70 kilograms, and that would be our predicted value. But our observed value in the scatter plot could have been a 6'4" person is equal to 73 kilograms. So that means our epsilon is 3 kilograms. Now this could happen the other way around. Maybe our observed value for 6'4" is 67 kilograms. And that would make our epsilon negative 3 kilograms. And what we're hoping when we have this linear model is that our expected epsilon is 0. So another way of saying that is that there will be a constant spread. So what that means is if we overestimate by, let's say in total, in our points, we overestimate by 10, we will assume we also underestimate by 10, and they even out, and then if we add them together, we'll get an expected epsilon of 0. Onto the criteria for a linear model. And there are two criteria in the advanced higher course spec, and that is the expected epsilon is 0. So we're assuming that as much as we overestimate, we also underestimate, and they cancel out. And also the variance of the epsilon is constant. And another way of understanding that is that visually, if you look at a scatter plot, it shows a linear relationship. So what do I mean by that? Well, here you can see that there's a linear positive correlation. Here you can see there's a linear negative correlation. But here, there may be a positive correlation, but it's not linear, it's curved. So that would mean that if we drew a best fit line here, first of all, it wouldn't be suited because it's not a linear relationship. But even if we did, which would not be right, the variance of the epsilon here is not the same as the variance here. So our variance being constant, that criteria will not be fulfilled, and therefore we shouldn't have and we can't implement a linear model. Now let's calculate the least squares regression line of y on x. The first thing we have to do here, well, let's work backwards. What do we need first? We need a, b, and epsilon. Epsilon we assume is 0, so we can ignore epsilon. We need a and we need b. We go here, we have a here, and we have b here. We need b to calculate a, so we'll try and calculate b first. So we need sxy and s double x. For s double x, we need the total of x and the total of x squared. And for sxy, we need the total of xy and then total of y, or sigma xy and sigma y. So I'll put sigma y here and sigma xy here, but we'll do that later. So how do we calculate sigma x? Well, we just add all of the x values. So that would be 27 plus 21 dot 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 plus 34. So I'm just adding all of these values. And when I do that, I get 160. Now, as the same with sigma y, we add 26, we add 34 dot dot dot, then we add 10. Don't do the dot 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 like I'm doing. I just don't have enough space in an actual exam or when you're even practicing. Write it out. And that gives us 144. So for sigma x squared, instead of this 27 plus 21, it's 27 squared plus 21 squared dot 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 plus 34 squared. And that gives us 4,426. Now for sxy, it's a bit difficult. So not a bit difficult, a bit pretty tedious. So what we have to do, we have to make a new row for xy. And then we add all the values we get. So 26 times 29, 21 times 34. And then you'd finish this row and then you add all of them together. I've made the xy row. So we can calculate sigma xy, which is equal to 702 plus 714 dot 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 plus 340. And that gives us 3,554. And now we have all the things required to calculate sxx and sxy, which is what we're doing to calculate b. So sxx is equal to sigma x squared, which is 4426, minus 160 all squared over n, and n is 6, it's the number of pair data. And for sxy, it is 3554 minus 160 times 144 over 6. So for sxy first, we would get negative 286. And for sxx, we would get 159.33. And with these two values, we can find b, which is sxy over sxx, so minus 286 over 159.33. We already know that the slope is negative, or it's a negative correlation because it's negative 286. And if I put this in my calculator, we get negative 1.8. Perfect. So we found B, and now we need to find A, and then we're done. So how do we find A? Well, A is equal to the average of y minus b times the average of x. So we need our averages. So we need x bar, which is 26.67, and then we need y bar, which is 24. A is equal to y bar, 24, minus negative 1.8 times 26.67, and that gives us 72.006, or I think we can just run it to 72, and that gives us the final linear model equation, which is y is equal to 72 plus, well, it's negative, actually, negative 1.8 x. This is what the graph looks like on Excel. You can see it's a roughly negative 1.8 gradient, and then you have these slight epsilons here, these gaps between our observed value and our predicted value through the linear model we've calculated. But overall, what we got looks decent. Now that is one type of question you can be asked. The other type of question you can be asked is calculating the least squares regression line of x on y. So before it was y on x. So that means that y depends on x. But if it's x on y, x depends on y, and we change our b formula. So in the core spec, the b formula for y on x is sxy over s double x. But if we're doing x on y, b is equal to sxy over s double y, not s double x. We've changed this to s double y because x depends on y. And it's entirely the same process, but b is a bit different, and I'll show you that here. To show the difference of x on y and y on x, I've used the same data, but it's just asking for a different b value, basically. So we have sigma xy, we have sigma y, we have sigma x. For this, we need s double y, and for that, we need sigma y squared here, this one. So how we would calculate that is 26 squared plus 34 squared all the way to plus 10 squared, and that gives us 3982. Next thing we need is s of s double y, which is 3982 minus 144 all squared over 6, and that gives us 526. For sxy, we already know what that is, which is negative 286. We have sxy, we have s double y. We can calculate b. B is equal to xy over s double y, which is equal to negative 286 over 526, which gives us the answer negative 0.54, which is a bit different to what we got when we did y on x. Now we need to calculate the linear model. We have b, we have x bar, we have y bar. So we need to calculate a, which is equal to y bar, which is 24, minus b times x bar. This gives us 16.4, and that means our final linear model is y equal to 16.4 minus 0.54x. This is a graph on Excel. It's much less steep as negative 0.54 is higher than the previous b value we had. And overall, it looks fitting for our equation. That is the end of the lesson. Now you should be able to know if a linear model can be fitted into a scatter plot just by looking at it. You should be able to calculate the least squares regression line of y on x and x on y. And you should be able to calculate s double x, s double y, and sxy.